Hey everyone, this video is about acceleration, a very challenging quantity in kinematics. Let me start by this introduction. Look at this car. Suppose that I read 2 meters per second on its speedometer. And then later, if I check the speedometer, it may change. You can see 6 meters per second, for example. So I can say the motion has acceleration. So roughly, acceleration indicates change in velocity. But it is not exactly the concept of acceleration. You should know more. So look at this car again. Suppose that at the time t equals 0, the speedometer indicates 2 meters per second. And if I check the speedometer in 1 second later, I see 6 meters per second. And if I check it in another 1 second later, I will see 10 meters per second. So in this case, the car is gaining 4 meters per second in each second. So change in velocity in each second is 4 meters per second. Now it is exactly the acceleration. So acceleration is change in velocity in each second. So acceleration is 4 meters per second in each second. If you integrate the 2 seconds because they are all in denominator, so I can write it also to be 4 meters per second squared. That's all. This is the concept of acceleration. But look at this case. It is also very interesting. Suppose that at the t equals 0, the beginning time, the car has a speed of 10 meters per second. But if I check the speed, it is 6 meters per second 1 second later. And then if I check it again 1 second later, I see 2 meters per second. So the car is decelerating. Basically, it's losing velocity. 4 meters per second in each second. Look at that. V2 minus V1 is going to be negative 4. So in each second, change in velocity is negative 4 meters per second. Now I can say the acceleration is negative 4 meters per second squared. So pay attention. Generally, the acceleration is change in velocity in each second. It could be positive, it could be negative. Now you may make a very, very big mistake. Is it okay to say that whenever the acceleration is negative, the object is slowing down? No, it is not true. Just in this case, yes, but it is not general. As the velocity in this case is positive and the acceleration is negative, yes, I can say it is slowing down or decelerating, but it is not general. Negative acceleration does not mean necessarily that the object is slowing down. Sometimes it is speeding up. I will have a full discussion in this video about this challenging part. Let's continue with uniform motion. Look at this car. For the time being, the car at t equals 0 has a speed of 2 meters per second. Let's say it's to the right. And then after 1 second, the speed is the same. Another 1 second, same. No change in velocity. Basically, it's a uniform motion. Can I say there is any acceleration? Of course, there is no acceleration, so I can say acceleration is 0. Keep in mind, uniform motion on a straight line does not have any acceleration. Acceleration is all indicating change in velocity. Uniform motion on a straight line can't have any acceleration. What about uniform motion over a curvilinear path? Suppose that the car is moving on a bumpy road, okay? At the t equals 0, the beginning time, the speed is 2 meters per second. But look at the car. It's not moving on a straight line. If I check the speedometer and if I see 2 meters per second 1 second later and again 2 meters per second 1 second later, you may make this mistake that the acceleration is 0 again. No, the acceleration is not 0. As the velocity is a vector and the direction of the velocity as a property of this vector is changing, I must know that this car also has an accelerative motion. So uniform motion on curvilinear path is always accelerated. But as in this video, we are just considering the straight line motion, we won't have any discussion about that. Later in another video, I will have a full discussion about two-dimensional motion. I will consider the properties of this type of motion in which the speed is constant, but the acceleration is due to the change in direction of the velocity. Now, if you agree, let's draw the velocity time graph for this car. This car has a constant acceleration. Constant acceleration means that the rate of change of velocity is always constant. In this case, it's 4. How the velocity time graph can indicate the acceleration for me? Let's start drawing the graph. At t equals 0, you see the velocity is 2. This is exactly the initial velocity, the vertical intercept of the vt graph. Another data point is t equals 1 and v6. So it's the other data point. And the last one, t equals 2 and v equals 10. Then I connect these points. I will get a linear vt graph. How the acceleration is found over a vt graph, I will show you how to do that. Just establish a triangle here in which the hypotenuse is part of the graph. And then let's find the slope. Slope by definition is vertical over horizontal, or rise over run. Rise is here delta v, which is 10 minus 2. In this case, it's 8. And the horizontal is 2 minus 0, which is exactly delta t. So if I divide 8 by 2, which is exactly the slope of this graph, I will find the acceleration. So acceleration is easily the slope of the vt graph. But it's not that easy. Let's have more consideration. Now please get ready to understand the concept of average acceleration. Suppose that the vt graph starts from t1 and v1 and ends at t2 and v2. But in general, it's not exactly a line. It could be a curve like this. Then I draw the secant line connecting these 2 points, the beginning and the ending point on the graph. And then I establish a triangle here to find and measure the slope of this secant line. Slope means vertical over horizontal, or rise over run. The vertical side of this triangle is delta v and the horizontal is delta t. If I divide these two, I will get delta v over delta t, which is exactly the definition of average acceleration. Pay attention, average acceleration is all independent of the behavior of the object in between the two moments. It's just related to the change in velocity in general and also the time interval. What do I mean? Look at this example, you will learn it. 3 velocity time graphs are given below. Which one shows larger average acceleration until t1? They all start from 0 and end at t1. Okay, look at this. The C, the B, and the A have all different behaviors in between the 0 and t1. But it's not important for me. For average acceleration, I will just consider the total change in velocity and the total time interval. So if I check it by a triangle, I see the vertical side is v1 minus 0 and the horizontal side is t1 minus 0. So it's the same for the 3 objects. I can say the average acceleration for the 3 objects is the same, equal. You see that average acceleration is not sensitive to the instantaneous behavior of the motion. But instantaneous acceleration is different. I will define it very soon in this video. Let's continue. I have a question now. This question is about the vector property of the acceleration. Is the acceleration a vector quantity? Yes, it is. But as we are in straight line motion, the vector is indicated by just a positive or negative sign. Let me tell you what is that. How can we find the direction of average acceleration? If it is a vector, it must have a direction. And on x-axis, which is one-dimensional motion, positive or negative indicates the direction. How can I find it? Let's go back to the definition. Average acceleration is delta v over delta t. You know that, okay? But delta v is v2 minus v1, and delta t is t2 minus t1. By definition in physics, you know that delta t cannot be negative, so it's always a positive quantity. The sign of acceleration, average acceleration, is all dependent on v2 minus v1. I should check if the v2 is larger than v1 or smaller than that. If the v2 is larger than v1, v2 minus v1 is a positive value. So acceleration is positive. So average acceleration is positive whenever the v2 is more than v1, larger than v1. And when v2 is smaller than v1, in general, I can say average acceleration is negative. Can I say positive average acceleration means the object is speeding up? No, I told you it is not true. Can I say that if the average acceleration is negative, the object is necessarily slowing down? No. I will tell you why. Be patient. Look at this. I'm gonna tell you what the instantaneous acceleration is. You remember we used this graph to explain the concept of average acceleration. What about the instantaneous one? You know, average means a measurement in a time interval. But to find the instantaneous acceleration, you should confine your delta t. You should shorten the delta t. The smaller the delta t is, the more we get to the concept of instant. So let's take T2 very close to T1. If I take T2 closer to T1 and if I establish my triangle again, I see the hypotenuse is going to be almost a part of the graph. But for the time being, it's not that good approximation. Let's go closer. Yeah, it's better, I think. T2 now is more close to T1. And so I can say the triangle as a hypotenuse, which is a part of the graph almost. And what if I take T2 very, very close to T1? Now I think the triangle is almost indicating exactly the slope of the graph because the hypotenuse is a part of the graph. So when T2 tends to T1, you know that it's defining the concept of the moment, instant. And so if I extend the hypotenuse of this triangle, I'm extending a part of the graph at that point. This is called the tangent line. The slope of this tangent line indicates the instantaneous acceleration. So in general, I can say instantaneous acceleration is a slope of the VT graph. For the VT graph like this, look at this, it's the VT graph, okay? Sometimes it could be like that. At this point, you know that the tangent line indicates positive slope. So here I can say acceleration is positive. Acceleration means instantaneous acceleration. And at this point, the acceleration is negative. Why? Because the slope is negative. So when you draw the tangent line, and if the graph is ascending like that, the acceleration is positive. When the graph is descending like that in VT graph, I can say the acceleration is negative. Let's continue. In the following VT graph, look at this VT graph. It's a very interesting example. Find the instantaneous acceleration of the motion at t equals 9. And the tangent line at t equals 9 is seen on the graph. This dashed green line indicates the tangent line on the velocity. And so the slope of the velocity time graph is exactly the slope of this tangent line. What should I do here? I should use this triangle here because I have an auxiliary point like 6 to help me to find the slope. So I establish a triangle here. A vertical here is 36 and the horizontal is 3. So if I divide 36 by 3, I will get 12. 12 meters per second squared is the slope of the graph or slope of the tangent to the graph. And this tangent line at this point has a special slope which indicates the acceleration at that moment. It is the instantaneous acceleration at that moment. Which moment? T equals 9. Because all I did was finding the acceleration at t equals 9. What about the part B? Find the average acceleration from t equals 0 to t equals 9. When they ask you about the acceleration in the time interval, they are indicating that they are mentioning the average acceleration. Average acceleration means you should draw the secant line. Secant line from where to where? 0 to 9. So from here to here, I will draw the secant line and then I try to establish another triangle in which the hypotenuse is exactly the secant line, and I try to find the average acceleration by finding the slope of the secant line. Vertical here is 36 and the horizontal is 9. So the secant line has the slope of 4, which is 4 meters per second squared. As you see, average acceleration from 0 to 9 is different from instantaneous acceleration at t equals 9. This is because the velocity time graph here for this case is a curve. If it is a line, it's not important. And anyway, the acceleration is always the same. Look at this one. The velocity time graph of an object is given in the figure. This velocity time graph is a little bit more complicated structure because from 0 to 2 it is a line, but from t equals 2 to 3 the line is horizontal, no slope I see, and then it is descending line. It's different, so I may have 3 different accelerations. Draw the acceleration time graph. Okay, to draw the acceleration time graph, I should check the slope in each time interval. First time interval from 0 to 2, I establish a triangle, and then I know that from 0 to 2, as it is a line, the acceleration from 0 to 2 will be the same. Constant acceleration from 0 to 2. It has partial constant acceleration. From here to here, I have delta t, which is 2. From here to here, I have delta v, which is 12. So 12 over 2 is 6. So from 0 to 2, the acceleration is 6, constant. From 2 to 3, there is no slope because the line is horizontal. So acceleration is 0. I draw a horizontal line on t-axis with no value because the acceleration is 0. The last part is different. It's a descending line. So I establish a triangle again. Vertical is 12 and horizontal is 7 minus 3, which is 4. So it's going to be 12 over 4. But pay attention, it's a descending line. So acceleration must be negative because change in velocity actually is 0 minus 12. v2 minus v1. So it's negative 12 over 4. It's negative 3. It's very interesting. Okay, so we considered also partial constant acceleration. As a whole, this graph does not have constant acceleration, but partially yes. So from 0 to 2, constant acceleration of 6. From 2 to 3, no acceleration. From 3 to 7, negative 3. Let's have a look on this xt graph. You see this xt graph is line. When it is linear, you know that the velocity of the object is constant. When the velocity is constant, there is no acceleration. Acceleration means change in velocity. Do you have any change? No. So it's not accelerated motion. But when the xt graph is kinked, when it's curvilinear, yes, there is necessarily acceleration. So it's accelerated motion. Why? Because the velocity is changing. Velocity is the slope of the xt graph, and the slope is all changing. What about a vt graph, which is a line? When the vt graph is a line, yes, it is accelerated motion, but you should keep in mind that acceleration is constant. What about this one, in which the velocity time graph is a kinked graph? Yes, it is also accelerated motion, but it's a variable acceleration. Later we will have a discussion over that in the coming videos. Okay, let's continue. Look at this one. The initial velocity of an object is given to be 20 meters per second and the acceleration is 4, okay? Velocity positive at the beginning, the initial velocity positive, and acceleration also positive. Acceleration is 4 means that the change in velocity in each second is positive 4 meters per second. So if the velocity is 20 at t equals 0, so at t equals 1, it will be added by 4. So it's 24. 4 plus 20. Now at t equals 2, we should add it by another 4. So it's going to be 28. Another 4 is 32. Another 4, 36, and so forth. Can I say that this motion is speeding up? Yes, because the speed of the motion is increasing. You know that speeding up means increase in the absolute value of the velocity or increase in the speed. Yes, it is speeding up. This case is different. Initial velocity is negative 20 and acceleration is negative 4. Both are negative. At t equals 0, the object is moving to the negative direction of x because it has negative initial velocity. When the acceleration is negative 4, means that in each second delta t equals 1, I will expect a change in velocity of negative 4. So at t equals 1, the velocity will be the initial velocity, which is negative 20, added by a negative 4. The change is negative 4. So it's negative 24. Okay, let's continue. I will add another negative 4 to negative 24. It will be negative 28. Then I will continue to negative 32, another negative 4, and negative 36 and negative 40. Is it a speeding up motion? Yes, because the speed is increasing. Forget about the sign. Speed is positive. So speed here is 24. Here the speed is 28. Here the speed is 32, 36, and 40. So yeah, it is speeding up. Let's continue. The next case is very interesting. Look at this. The initial velocity is positive, but the acceleration is negative. What should I do? Okay. At t equals 0, the velocity is 20. At t equals 1, the velocity will be initial velocity plus negative 4 because the acceleration is negative. So it will be 20 minus 4, which is 16. Let's continue. I will add another negative 4 to 16 and I will get 12. Another negative 4, I will get 8. Another negative 4, I will get 4. Another negative 4, I will get 0. Interesting. The object is stopped here. Then if I add another negative 4, the velocity will be negative 4. Another negative 4, negative 8. Another negative 4 is added by negative 8 and you will get negative 12. It is very interesting. So it changed direction of motion. From t equals 0 to t equals 5, the object has positive velocity. The velocity is positive. And after that, the velocity is negative. Change the direction of motion. How can I judge the speeding up or slowing down? It's related to the speed. Here the speed is 16, 12, 8. Okay, the speed is decreasing. So from here to here, it's slowing down. And then after 0, you see the speed is 4, the speed is 8, the speed is 12. So it's speeding up. Yeah. How should I find the slowing down or speeding up of the motion in general? I have a special offer for you. Look at this. I offer to have AV. Let's multiply A by velocity, acceleration by velocity. And let's check it. Acceleration is always negative in this case. So to find the AV at V equals 16, I will multiply negative 4 by positive 16. It will be necessarily a negative value. AV, whatever it is negative. Again, negative 4 multiplied by 12 will be a negative number. Negative 4 multiplied by 8 will be again a negative value and again a negative value. Then negative 4 is multiplied by 0, it's 0. Then negative 4 is multiplied by negative 4, it is positive. Negative 4 multiplied by negative 8, positive. Negative 4 multiplied by negative 12, it's again positive. Look at this. When the object is slowing down, AV, acceleration times velocity, is negative. And whenever the object is speeding up, AV is positive. So it's a very good criterion for you to check if the object is slowing down or speeding up. Look at this case. Again, at the moment, now, in the case 1, acceleration is positive, velocity is positive. Exactly at this moment, can I say that it's speeding up? Yes, because both have the same sign. Here, AV must be positive because acceleration positive times a positive value of velocity, positive. Yeah, speeding up. Look at this one. Here, the velocity is positive, but acceleration is negative. So positive times negative, AV will be negative. AV negative, so it's slowing down. This case, acceleration negative, velocity negative, both negative. If you multiply them, you will get again a positive value. So it's speeding up. AV here is positive. The last case, acceleration positive, velocity negative. If you multiply a positive by negative value, you will get negative. So AV here is negative. So it's slowing down. Look at this. The sign of acceleration in one-dimensional motion indicates direction of net force acted on the object. You may know about Newton's second law of motion. We know that if we have a mass of m and if it is acted by a net force of F, the acceleration of this object is going to be force divided by mass. So F equals ma. F is the net force acting on the object, and m is the mass of the object, and a is acceleration. As the mass is always a positive value in physics, acceleration and force will have the same sign, same direction, because we are in one-dimensional motion, so direction means sign. Positive to the positive direction, negative to the negative direction. So whenever the acceleration is positive, we can say the force is positive. So the object is acted by a net force to the positive direction of x. And whenever the acceleration is negative, the object is acted by a net force to the negative direction of x. Look at this case. Here, acceleration is positive. Immediately, I can say the net force acting on this car is to the positive direction of x. Let's say it is positive direction of x. And the other, when the acceleration is given to be negative, the force necessarily will be to the negative direction of x. If this is positive direction of x, force must be to the left. Okay? What about the speeding up or slowing down? It is different. Slowing down or speeding up is all related to the simultaneous product of acceleration and velocity. I should know the velocity for each case to know that if it is speeding up or slowing down. Let's say the velocity in the first case is positive also. Oh, okay. If it is positive, as the acceleration is positive, the multiplication will be positive, so it's speeding up. What if the velocity is positive, but the acceleration negative? You know that. It is slowing down. So to judge about the speeding up or slowing down, don't rely on force, don't rely on acceleration, absolutely no. You should consider the direction of force or acceleration simultaneously with the velocity. Okay, the last part is the area under the acceleration time graph. Look at this VT graph. It's a very easy case in which the velocity has a constant change. Acceleration is constant, you know, because it's a linear graph. Initial velocity is 4 and the final is 14 in 5 seconds, okay? I'm gonna draw the acceleration time graph. Acceleration is the slope of this graph, and it's very easy because it's just a line. I establish a triangle. Rise is 14 minus 4, which is 10, and the run is 5. Rise over run, 10 over 5, the acceleration is 2. It's all 2 from the beginning to the end. Okay. Let's continue with something very interesting. Suppose that I'm gonna find the area under the acceleration time graph, means the area confined between the acceleration graph and the horizontal axis, the t. So the area confined between the acceleration time graph and the t graph or t-axis is going to be the area under the graph. This is a rectangular area, so width, which is 2, times the length, which is 5, will be 10. So the area under the graph is 10. Okay, what does it mean? Look at the VT graph. You see the velocity starts from 4, goes to 14. The increase in velocity, change in velocity, is also 10. It's very interesting. So you must know that area under the AT graph, acceleration time graph, is always change in velocity. Can it be negative? Yes. Change in velocity can be negative, can be positive. It depends. For instance, suppose that the VT graph is given like this. Okay, part of that is above the t-axis, part of that is below the t-axis. What should I do in this case? Okay, suppose that here the area under the graph is maybe 23, and here the area under the graph is, let's say, is 3. Okay, what does it mean? Means that from 0 to t1, the change in velocity is 23, and from t1 to t2, the change in velocity is negative 3, because the area below the t graph indicates negative change. So totally from 0 to t2 here, I can say the change in velocity is going to be 23 minus 3, which is 20 meters per second. It is very important. So in general, the area under the VT graph is change in velocity. If the VT graph is given like that, the area above the t-axis indicates positive change in velocity, so delta v is positive, and the area below the t-axis indicates negative change in velocity, so delta v is negative. That's all. Again, I'm really thankful to you because of being with me. Take care and review the lesson. See you in the next video.